Okay, so sorry about the delay. Should be okay now. So as I said, hi, I'm Dana. I'm from the Technion. I will present a work called Learning Disjunctions of Predicates. And this is a joint work with Nader Bashuti, Martin Vetchev, and Eran Yahov. So what is this work about? So there are many works that study the concept of learning from membership queries. And what we do is consider a new setting of learning from membership queries in the setting of programming by examples, which is a subsetting of program synthesis, which I'll explain in a bit. And this new setting introduces new challenges in exact learning, and we show first results in this setting, and we hope this will be interesting to other problems in this setting. So what is program synthesis? So program synthesis is the task of generating a program from a high-level specification given, for example, in the form of mathematical formula. So let's have an example. So let's look at Efteling, which is an amusement park, and say that it opens a new roller coaster ride that has some height limit of at most 1.5 meters. And what Efteling wants to do is to advertise this to his child and female visitors. So he has a list of the names and the gender and the age, and they infer all these properties or predicates, if you will, like he's male, he's female, he's adult, he's man, he's woman, he's child, he's boy, or he's girl. Okay, so as I said, they want to send emails only to the children and to the females. So what program synthesis led to do is to provide some mathematical formula of what you want to do, then give this to the computer, which will look for a program satisfying this formula, and then it will produce a low-level program. This wasn't me. Okay, so this is very nice. But the thing is that most computer users, and most likely the advertisement group Efteling, don't know how to write mathematical specifications. So this has given rise to programming by examples, which is a subset of program synthesis where the user can describe her intent through a set of input-output examples. So the nice aspect about this is that the user doesn't need to know how to write mathematical formulas. And this is why this subfield is believed to have broader impact. So how does it look in PBE? So the user provides input and output example. For example, Sophia is a female at the age of 20. We want to send her the email. Same goes for Aidan, who's a male at the age of 12. We want to send him an email. In this case, what PBE algorithm will do, will look for a program that meets these examples, namely a program consistent with these examples. And this means that this might lead us to an incorrect program. So why this happened? Well, examples underspecify user intent most of the time. And the thing is that the users are not programmers. They can't look at the program and say, this is incorrect. So the question that we ask is, when we learn the exact user's intent? And this is our approach, exact PBE. So what we want to do is to learn the exact user intent through membership queries only. And what we will do is model the user intent as a formula over an arbitrary set of predicates. Specifically in this work, we learned the class of disjunctions or dually conjunctions. So how does it look now in the exact PBE? The computer wants to learn the user intent modeled as a formula, so it will generate some membership queries. The user will respond yes or no, until at some point the computer has learned the user's intent, and now it can look for a program satisfying the specification as we had before, and this is why now this is guaranteed that the program learned is correct. Okay, so how do we do this? So formally, we want to define the following problem. We are given a set of Boolean functions or predicates, and we want to learn the class of disjunctions over these predicates from membership queries. And what we do is show an algorithm that poses at most f, which is the size of the number of predicates that we have, times the optimal number of membership queries. And our algorithm runs in polynomial time when the set of predicates is either a set of half spaces over a constant dimension or a set of variable inequalities. So what is the idea? If we want to look for something, we first need to define the search space. So what is our search space? So an interesting thing happens when you want to learn formulas over an arbitrary set of predicates, and that is that some formulas are logically equivalent to one another. And the first thing that we note is that this induces an equivalence relation. So in our example, is adult is logically equivalent to is man or is woman. This means that they have the same equivalence class. So we don't want our search space to contain all the formulas in our word, just representative of them. So what would be the representative? So we define them to be those formulas in the equivalence class that any predicates to them will make them non-equivalent to the formula it had. So, for example, the representative of is adult and is man or woman is the disjunction is adult or is man or is woman. Okay, so now we have decided what are the nodes in the search space, and how we define the edges is as follows. So we define a partial order over the representative, which is the logical implication. So, for example, is adult or is man or is woman logically implies is female or is adult or so on. Okay, so let's look at the Hasse diagram. So at the top we have the formula that contains all the predicates, and then below we have formulas that have fewer predicates. At orange, this is our target formula from the example, if you remember. And this graph continues until it reaches the contradiction. Okay, so how do we search in this search space? So we introduce a notion of a witness, and a witness of a parent-child pair is an example satisfying the parent but not the child. So let's have a look at this. So this is the example that we had before. So for this top formula and this child, this is a witness because this is a female child. That is, it meets this specification, but not that one. Okay. The interesting aspect to note is that for each child there is a different witness. This also will give us the lower bound. Okay, so now we can quickly review the algorithm. So what do? We start at the top node. At each moment we have some node. We go over its children. We present the witnesses and accordingly decide whether the target formula is reachable from any of the children. So let's see how it goes. We start at the top. We look at one of the children, and then we create our witness, and this happens to be a negative example. So what we do, we prune that node and all of its descendants. So we will record this to a set T. And then we move on, and here we also have a negative example. So we also record this. Same goes for the third child. And now we reach to the target formula, which obviously will be a positive example because we know that in this case the target formula is reachable from that node. So what we do, we continue with that node in a recursive call, and now we look at its children. So when we look at its children, these are pruned by the other nodes that we already pruned. And this is why at this point we know that the target node is reachable from that node, but not from any of those. So this means that this is the target node that we want to learn. Okay, so we also show a lower bound. So we show that any learning algorithm that learns our class has to oppose at least the maximum between the logarithmic number of the number of nodes that we showed and the maximum number of children that any node in the graph has. In particular, our algorithm called SPEC poses at most number of predicates times the optimal number of membership queries. In a high level, what happened is that, well, this is from the information theoretical bound, and this is because if the target node is the one to have the maximum number of children, then obviously we need to present a query for each one of its children. So what we show is that at every invocation of specs, the number of membership queries that we will present is bounded by the number of children that the node has. And the number of invocation is bounded by the height of the Hasse diagram, which is at most the number of Boolean functions that we have at hand. So there are a lot of missing points in the description that I just showed. For example, how do we obtain the node's children? How do we efficiently compute the witnesses? How do we obtain polynomial algorithm for particular settings? And there are a lot of interesting details, so you are welcome to read the paper or come now to the poster session. So that's it. So just to conclude, we studied the problem of learning from membership queries in a new setting. And what we learned is disjunction or dual conjunction. So this is applicable to program synthesis, but we expect this to be applicable to other domains as well. And there are some open problems like how do we learn the class of DNF formulas from membership queries and whether we can improve the lower bound of our algorithm. So this is it. So thank you for your time, and I'll be happy to take questions now. Thank you.
Is it conceivable if the factor of the family F could be removed?
Sorry, could you repeat?
The size of the family factor in the number of queries, is it conceivable that that could be removed?
You mean in the lower bound?
No, in the algorithm. Or do you have
In the algorithm, in what I showed in that part?
the size of that factor.
That?
Is that necessary?
We don't know. I mean, we haven't shown, I mean, this is the lower bound that we show, so obviously there is some gap here that we still don't know, but it might be interesting to look at it. Yes, thank you.